Okay, hello chemistry students. This is a video lesson for Tuesday, September the 25th. Unfortunately, I am absent unexpectedly today. My daughter had a ear infection and I had to stay home and take care of her today since you can't take your kid to daycare when they have a fever. So first thing I want to just note is, before I start, if you had any trouble with the homework, with the lesson for average atomic mass, I'm going to insert a link to another video lesson from Tyler DeWitt from his channel, just to go over that stuff in case you need extra help. Most of y'all, when I checked yesterday, looked pretty good on that, but just in case, I'll put that link in. And again, just to clarify some things in the packet that you are not responsible for this unit, the next couple of pages, so page 9, you can just go ahead and cross that out. We're not doing this average atomic mass lab. So that's also going to be page 10. Page 10 and page 11 you can go ahead and cross out. I know you love to cross stuff out in your packet. Feels really good, probably. Okay, so page 12, don't cross this out. This is what we're going to start on today. All right, so I'll go ahead and load the PowerPoint. We'll go through the definitions on this page. I want to say this stuff is really important. Really, please pay attention to this lesson because this is definitely going to be covered on the test Thursday. Test is still the same day. You're still responsible for it, guys. So really try to focus on this stuff as we go over it today. Okay, so today's topic is nuclear chemistry. And so basically it's about the chemistry of just the nucleus of an atom. Most of chemistry, as we'll see the rest of this year, really happens with the electrons outside the nucleus, but there are some interesting things that happen in the nucleus as well, and that's what we're going to focus on today. So these are just three individuals who are very important in terms of their work on nuclear chemistry. They're all French, Henri Becquerel, and then Marie and Pierre Curie, who were married, why they have the same last name. All three won Nobel Prizes in physics for their work with nuclear radiation. So what causes radiation or nuclear decay? And this is the top of page 12. It's the presence of too few or too many neutrons of a nucleus. So you can think of neutrons, they're kind of like the glue that holds the nucleus together. If you don't have enough glue, then the nucleus will be unstable and it will break apart. All right. Also, if you have too many neutrons, then the nucleus can sometimes break apart. Simply, sometimes the nucleus can be just too big. It can have too many protons and neutrons in it, and so it will break apart. It will become unstable. So atoms are kind of like Goldilocks. They don't want to be too big or too small. They don't want to have too many neutrons or too few. They want to have just the right amount in order to be stable. If they're unstable, then they will decay, which we'll talk about today. So just a review, when we do talk about nuclear equations in a little bit, we always write everything in isotope notation. And so when we do that, we put the symbol here. We just write it out with the letters from the periodic table. But we're always going to have these numbers. So remember, mass number is your protons plus your neutrons, and your atomic number is just your protons. All right, so just some definitions. I'm going to just throw these up here. You can write them down, pause the video if you need to. But radioisotopes are simply isotopes that have an unstable nucleus. So the nucleus is either too big or doesn't have the right ratio of protons to neutrons, so it's going to break apart. Okay, some other definitions, and again, pause this if you need to write these down on page 12. But nuclear reactions are simply reactions where those unstable isotopes become stable. They gain stability by changing. Okay, radiation is the energy that is released when nuclear reactions occur. They always are accompanied by a large amount of energy being released from the nucleus of the atom. Transmutation, all right, so that's when one element changes into another element as a result of a nuclear reaction. So this only occurs when the number of protons in the nucleus changes, which we'll see occurs with two of our types of nuclear radiation or decay. So if you have a radioisotope that's unstable, it's going to undergo a kind of nuclear reaction, and after that reaction, or during that reaction, there will be some radiation, some energy that is released from the nucleus. So our last definition on page 12 is radioactive decay. So it's simply the process where an unstable nucleus loses or emits some energy by emitting particles of radiation. And there's a couple of types of particles that you'll have to know about. The first type of particle that can be emitted is an alpha particle. So we call this type of decay alpha decay. And so an alpha particle is simply a helium nucleus that is emitted. And it's a helium nucleus because it has a mass number of 4 and it has an atomic number of 2. So it contains 4 total mass particles. It's got 2 protons and 2 neutrons. If you subtract, you can get 2 neutrons. The symbol is simply the letter alpha. It's a Greek letter. And here is an example of a nuclear decay where I have thorium, the element thorium, which is an unstable isotope, with a mass number of 230 and an atomic number of 90. And we can see that it is releasing an alpha particle, a helium nucleus with a mass number of 4 and an atomic number of 2. So this is the particle that shoots out of the nucleus of the thorium atom. And think of this is like a mathematical equation. You can think of this arrow like an equal sign. So the top numbers have to balance on both sides of this arrow. So if this thorium nucleus emits an alpha particle, the mass number is going to go down by 4 because this part is leaving the nucleus. So if I take 230 and I subtract 4, well, what mass number is left? It's 226. So this is what the new nucleus of the thorium atom is going to look like. All right, now the atomic number was 90 before the alpha particle got emitted, but since the alpha particle contained 2 protons, then the atomic number rather, is going to go down by 2. I take 90, subtract 2 from it, and I have 88 protons left in the nucleus. So that's why you can figure out, even if you weren't told what element it is, it's going to become radium, because the number of protons went down by 2. But notice again that all of these numbers balance. 2 plus 88 equals 90. 4 plus 226 equals 230. Second type of decay is called beta decay. And this occurs when a neutron that is in the nucleus of an atom converts into a proton and an electron. And that's kind of an odd thing to think about, but that's exactly what happens. Now the electron is emitted, which means it shoots out of the nucleus and goes off into space somewhere, but the proton stays behind. It's still part of the nucleus. So the particle is represented with this symbol with a little e that stands for the electron. The mass number is 0 because remember electrons have 0 mass, so there's no mass that's leaving the nucleus. But it has an atomic number of -1, which is kind of odd if you think about it, but we're going to see this is necessary to balance the nuclear equations. The symbol is the Greek letter beta, which kind of looks like a cursive B, with a little tail on the end. And here's an example of a beta decay equation. So we start with the isotope carbon-14, which has too many neutrons. It has 8 neutrons in the nucleus and only 6 protons. And that's not really a stable arrangement. So carbon-14 doesn't last permanently. It's going to decay over time. And so it emits a beta particle. That beta particle has 0 mass number. So I can take 14 and subtract 0. Well, I still get 14, right? There's still 14 particles in the nucleus. It's simply that one of these 8 neutrons is changing into a proton, but it still is the same mass number. However, notice that your atomic number here is -1, right? So remember what we said is a neutron is changing into a proton. So this carbon atom had only 6 protons, But since one of those 8 neutrons changed into a proton, the atomic number goes up by 1. And mathematically, this still balances out. 7 plus -1, that's equal to 6. Right? Or you can just say 7 minus 1 equals 6. Right? So my top numbers still balance, and my bottom numbers, my atomic numbers, still balance out. That's why this number has to be a -1 here to balance out your nuclear reaction. Our third type of decay is gamma radiation. Now, gamma radiation is just pure energy. It has no mass and no electric charge. Has very high energy, and it's the most dangerous type of nuclear radiation. It often accompanies or goes with beta or alpha decay at the same time. The particle is this Greek letter gamma. Kind of almost looks like a cursive Y. And that's our symbol. Okay, but there's 0 mass and 0 atomic number. There's 0 charge. So if I have a carbon-14 nucleus and it emits gamma radiation, since the numbers are 0 and 0, then the thing that's left after the gamma particle leaves, or the gamma radiation, is exactly the same. It's still carbon-14. So this is not changing. This is not a transmutation reaction. All right. Now, number 2 is actually, if you take a look at it, just this part here. If I ignore the gamma particle at the end, this part here is just a beta decay, just like what we looked at a minute ago. I've got potassium with an atomic number of 19 and a mass of 42. It has too many neutrons, so it converts one of those neutrons into a proton. So the atomic number goes up to 20. The mass number stays the same, and it emits a beta particle. But at the same time, it also emits gamma radiation, which really the numbers are still 0 and 0 here. So notice that this still just all balances out. 42 minus 0 is still 42. 19 minus -1, that goes up to 20. Right? So your nuclear equation overall still balances out. Okay. Transmutation, this is just a reminder of the definition. You already wrote this down, so you don't have to write it again. But it's basically when a nucleus becomes a new nucleus. It becomes a nucleus that is different. Why is it different? Because the number of protons is changing. All right, so the only type of radiation that does not change the atomic number of the 3 that we looked at, okay, we looked at alpha, beta, and gamma. Well, notice what was the only one of those that didn't change the nucleus, that didn't produce a new element? It was gamma, because gamma has no mass and no charge, so it doesn't affect the type of nucleus that you have. All right. This cartoon just kind of illustrates the penetrating power. That is the ability of these particles to go through different types of material. So if you'll notice, this down here is easier to look at. An alpha particle is not able to penetrate through a sheet of paper. So alpha particles, even though they're radioactive and they have some energy associated with them, they're easy to stop, right? Beta particles can go through paper, but not through a little bit thicker substance like wood. But a gamma radiation particle is extremely high energy, so it can easily go through paper. It can easily go through wood. It can only be stopped by fairly thick concrete or lead. All right, so gamma particles by far have the most energy and the most penetrating power. So just pause the video for a moment and take a little bit of time to fill out this chart on page 13 of your packet. That just compares and contrasts the 3 types of radiation. And make sure you memorize this chart, because I can guarantee you that there will be multiple questions on the test Thursday that cover this information. Okay, once you've completed this chart, take a moment just to do the review questions at the bottom of page 13. And basically all you're going to do is just fill in the type of particle of radiation that matches those descriptions, and then we'll go over the answers. So pause your video for a second and fill in the bottom of page 13, and then you can review your answers. You can ignore this homework thing right now. We still have a little bit left to do. So first, let's go ahead and review the answers real quick to the bottom of page 13. What's the most dangerous type of radiation? Well, the most dangerous is going to be the one that has the most energy. So what would that be? That would be gamma, which is kind of that symbol right there, but that's a gamma particle. The largest of the particles, the one with the most mass, that's going to be an alpha particle. Which particle has a positive charge? All right, well, that would also be an alpha particle. The charge of an alpha particle is +2. What has no mass? Well, there's two answers for that. Gamma particles have no mass, but since a beta particle is just an electron and we say electrons have 0 mass, you could also say that a beta particle has no mass. What's a helium nucleus? That would be an alpha particle. What can't penetrate paper or clothes? That would be an alpha particle. What's only harmful if it's ingested, which means like you swallow it or breathe it in? Well, if you think about the penetrating power of these three particles, right? Alpha has the least penetrating power. So as long as it's outside of your body, if you have a source of alpha particles, it's not going to hurt you. But if you ingest it, if you swallow it, then this can be extremely harmful because it can still get into your body that way. So an alpha particle is only harmful if it's ingested. Beta particles, so a chemical substance that's emitting beta particles, is still dangerous even if it's outside your body because it can probably go through your clothes. Gamma radiation is pretty much dangerous no matter where it's coming from because it can go through virtually anything. You don't have to swallow a gamma particle source for it to hurt you. It can be in the next room, or it can be in the next county, or it can be on a star that's millions of light years away, right? It can still do damage to you if you're exposed to it. All right, so let's go ahead and flip over to page 14. And we're going to look at some examples of how to write nuclear equations. Okay, so I'm going to flip back to the PowerPoint real quick. All right, so just pause your video for a moment to write down. This is the description at the top of page 14. All right, and so a nuclear equation is going to look like this. You're going to have some isotope that is present before the reaction. You're going to have an arrow, and then whatever is over here is what's present after the reaction. You're going to have some particle emitted, either an alpha particle or a beta particle, or it could be gamma radiation. Plus, you're going to have some element. Now, the element is whatever is left over after the isotope loses the particle, right? But when you write your equation, always balance your mass numbers first. That's the numbers that are up at the top, followed by your atomic numbers, which are your numbers that are down at the bottom. Because of the law of conservation of mass, all of those numbers, the mass numbers and the atomic numbers, have to balance out on either side of the arrow. So you can think of the arrow like it's an equal sign in algebra. Okay, so let's go ahead and take a moment just to work through our problems on our examples on page 14. All right, so I'm starting out with this element here, which is Pu. That's plutonium, and it has a mass number of 239 and an atomic number of 94. What's it going to do? Well, it's going to do, this is an alpha particle. You have to memorize these particles. This is an alpha reaction. All right, and I want to know, I have to be able to predict, well, this is my particle that's emitted. What is the new element that I'm going to get? Well, don't worry about the symbol of the element yet. Worry about the numbers first. I'm going to take 239, and then I'm going to subtract 4, because that is what's being removed from the nucleus of this plutonium atom. So 239 minus 4, what's that? Well, that's 235. That'll be the new mass number. What'll be the new atomic number? Well, 94 minus, it's losing 2 protons. So it's going to have a mass of 92. I'm sorry, not a mass, that's the atomic number. So 235 over 92, well, what do? I go ahead and look up what the new element's going to be. So I just need to look up, there's the atomic number, 92, so I can flip to a periodic table. Here's conveniently one on my desktop. And atomic number 92, okay, I look, okay, it's down here. It's uranium. So uranium is going to be the new element that is present. So plutonium emitted an alpha particle and it became uranium-235. Okay. Next, this time I've got potassium with a mass of 42 and atomic number of 19. And this time I'm not given the particle. I'm given the new element that's left behind, but I don't know what the particle is. Well, again, we just have to make sure that we make the numbers balance. Well, if I have a 42 on top and a 42 on top, well, my number that's in the middle is going to have to be 0 because I want those to balance. They're already balanced, so I better not change anything. I better make that a 0. Now, on the bottom, I've got a 19 over here and a 20 over here. So what do? I just take 19 minus 20. What's that? That's -1. So what does that make? That matches our description of a beta particle from our notes. So I can just, a couple ways. You can either write the letter B, okay, for beta, or you could also just put, if you want to, you can just put a little E next to that. Okay, either way you write it symbolizes that you have a beta particle. So that is an example of a beta decay. Okay, well, let's take a look at our third one. 235. Okay, I have uranium here with a mass of 235. Now, after the reaction, I still have a mass of 235, so I put a 0 on top. I have an atomic number of 92 before and after the reaction. So my atomic number didn't change. What kind of particle is that? That would be a gamma particle. So that would be a type of gamma decay. All right. Now, usually these are pretty easy. Students don't seem to have trouble filling in blanks when you're given a blank in a nuclear reaction. Sometimes people have more trouble with like number 4, number 5, where it just says write the equation of this doing an alpha decay or a beta decay. All right, so you just have to be a little bit more disciplined to do this, but it's basically the same thing, right? I know that I have lead 210. Remember when it's written out like this, that number that it gives you, it's not the atomic number, that's the mass number when it's written out in isotope notation. So how can I know what the atomic number is? Well, since it tells me the element, I can just look it up on the periodic table. So I'll just pull up my periodic table again. It says that it's lead. Lead is down towards the bottom because it's a really heavy element. There it is right there. Okay, it's Pb. If you kind of remember lead is like peanut butter, then maybe that helps you. All right, so I can see the atomic number is going to be 82. All right, so I've got lead 210. Okay, that's going to give me 210 on the top and 82 on the bottom. All right, and that's what I'm starting with. Now, what's going to be present afterwards, I draw my arrow, okay, and I'm going to have an alpha decay. So you have to memorize, well, what is alpha decay? Alpha decay is when you have a helium nucleus, so He, with a mass number of 4 and an atomic number of 2. So this is what's getting shot out of the nucleus of our lead atom. Okay. Then I'm going to go ahead and add my next thing. Okay, well, what's going to be present after the helium nucleus leaves? So this is just where I subtract 210 minus 4. What's that? 206 will be my new mass number. It's going to go down by 4. 82 is my atomic number. I had 82 protons in the lead nucleus. I'm losing 2. So what's going to be left? Going to have 80 protons left in the nucleus. Okay, so then I look up, what's my new element going to be? I use my atomic number down here. So I look that up on my periodic table, and it was 80, right? So 80 is going to be mercury, Hg. Okay. You'll kind of notice a pattern. Whenever you have an element that undergoes alpha decay, it always is going to just move down the periodic table by 2. So we started out with lead, and we went to mercury. See, we went down by 2 elements, right? If mercury did another alpha decay, then you would get platinum, right? If platinum did an alpha decay, you get osmium, but you always move down by 2 elements. All right, take a look at number 5. So we're going to do that same element. We're going to start with lead 210. So I can actually just write the same thing here. Pb with a mass number of 210 and an atomic number of 82. And it's going to undergo beta decay this time, beta particle. So a beta particle has a mass number of 0, and it has an atomic number of -1. It's essentially just an electron. Okay, then I'm going to add my resulting element over here. I'm going to get a new element, right? So what do? Well, I take 210 and I subtract 0. So 210 minus 0, well, what's that? Still 210. Your mass, when you do a beta decay, does not change. Stays exactly the same. Now this is the tricky part, right? Up here with our alpha, we took 82, subtracted 2, we got 80. We always subtract when we want to find the new particle that we get, or the new element. So I still need to subtract 82 minus -1. Remember, when you subtract a negative number from math, what do you actually do? You're actually turning it into a positive, right? So 82 minus -1, my atomic number goes up by 1. Now I have atomic number 83. And that's because one of these neutrons, there's a lot of neutrons in this nucleus, but one of these neutrons is converting into a proton. So the mass number doesn't change, but the atomic number jumps up by 1. And so what does that do? It gives me an element that's 1 proton greater than lead. So I can look that up on my periodic table. There's lead, goes up by 1. So now I have the element bismuth. Bi is my correct symbol. Okay. Last one, number 6. Show the transmutation of uranium-237 as it undergoes alpha decay. What is the nuclide that's produced? Nuclide just refers to the new element that is made with all of these things. So for this process, my nuclide, this is my particle, and then this is my nuclide. That's just basically what's the new nucleus that's left after the particle gets emitted. So 6 is really telling us just to do the same thing. So I'm starting with uranium-237. My symbol for uranium is just a capital U. That is my mass number, 237. Okay, and what's my atomic number? Well, I need to look up uranium real quick. I know it's down here at the bottom. It's number 92. And it's going to do an alpha decay, it says. So the particle is going to be your helium nucleus, mass number of 4, atomic number of 2, plus what's my nuclide going to be? So again, to do this, you're just going to subtract your mass number first. 237 minus 4 is 233. Your atomic number, 92 minus 2, is going to be 90. And what's my nuclide going to be? Well, I use my new atomic number to look that up on the periodic table. Like we said, it always goes down by 2 with an alpha decay, so my new element's going to be thorium. Okay, so hopefully that helps you out a little bit. Your homework assignment, which is still due tomorrow on Wednesday, is going to be to complete all the questions on page 15. All right, so for each of these, make sure that you write out the equation. So make sure that you do exactly what I just did in the examples. So start out by figuring out what do you start with. Sometimes it'll just tell you. Sometimes it'll give you the element name and the mass number, and you have to write out the symbol yourself. All right, but you'll definitely need a periodic table as you do this. So either look one up on your phone or use the one that's in the back of the packet if you can read it. But make sure that you take care of this, And remember, guys, we do have a test coming up on Thursday. So the review, which is in the back of your packet, okay, the review starts on page 19 and goes through page number, I think it's 22. Oh, I'm sorry. The review goes all the way to page 20. Ooh, it's a long one. Okay, review goes to page 26. Right, so page 19 through page 26. Make sure you go ahead and start on that early. Start on it ahead of time because it is due on Wednesday. All right. So hope you got something positive out of watching this video. And also check out the links that I inserted. I inserted a couple of lessons from Tyler DeWitt's channel along in the video at a couple of spots. If you're having any trouble with this, then make sure if you have trouble with this homework, go back to those places where I put the link into Tyler's channel and watch some of his lessons on alpha and beta decay. He goes into a couple more examples, and that might help you out. Okay, guys? So thank you for watching, and if you watched all the way to the end, leave your name and class period in the comments at the bottom, and that just lets me know that you did watch the whole video. Okay, so thanks for watching, and I will hopefully see you on Wednesday.